Okay, so welcome to this presentation. Today I'm going to be talking about reactive web development with Play on Java 8. So my name's James. That's a picture of me working in my office in Australia. Real estate's expensive, so it's a pretty small office. But no, I work for a company called TypeSafe. TypeSafe is the company behind Scala, as well as Akka and Play Framework. And we're also one of the main drivers of the Reactive Manifesto, which is one of the reasons why I'm talking about reactive web development today. So as you may have guessed from my accent, I'm Australian. I come from Sydney, and I'm still a little bit jet lagged, so I'm hoping I'm still awake by the end of this presentation. So can I get a feel, has anybody here started using Java 8 in production or in development anywhere? Nobody? Is anybody here interested in Java 8? Okay, good, you're in the right presentation. And has anybody here used Play? Okay, a few. Okay, so what I'm going to be talking about today, I'm going to first talk about Reactive and Java 8 and why these two things are quite related and what Java 8 brings to reactive development. I'm going to talk a lot about promises. I'm going to be talking about a few other things, a few other reactive things like Akka, but there'll be a number of demos along the way. And at the end, just to put you to sleep so that you don't remember anything else apart from what I said today, I'm going to talk about monads. So, who here has heard of the Reactive Manifesto? Anybody signed it? Okay, so the Reactive Manifesto, it's a manifesto. Here's the website. What it is it's a recognition that applications today, the needs are changing and the way our current, many of our current technologies work are not evolving fast enough to keep up with these needs. So the Reactive Manifesto has 4 tenets. One is event-driven, so that is primarily about things being asynchronous I/O, things responding to events rather than you requesting something and waiting for it to happen. The other 3 tenets are scalable, so scaling out for internet loads, resilient, so if part of your application fails, the rest of it shouldn't fall over, and responsive, which is about being responsive to users, so not making them wait, giving them data as soon as it's available. But primarily today I'm going to be talking about the first tenet, which is event-driven. And the reason why I'm talking mostly about event-driven in the context of Java 8 is because event-driven generally means callbacks. So in a traditional stream, you like an input stream, you might call read to read a byte, and then you wait for that byte to be available and you get it. But in event-driven streams, or in anything that's event-driven, instead of calling read and then waiting, you call read and pass a callback or some sort of way of handling that in future that doesn't involve you having to wait. And so this is where Java 8 is really important because it gives us lambdas. And lambdas are a really nice way to capture this logic that will get executed asynchronously at some point in the future. So I'm guessing most people here have heard about lambdas and maybe even might be familiar with the syntax. If you're not, that's all right because I'll be showing you a lot of lambda syntax in the rest of the presentation. So there are a lot of ways to I guess, express asynchronous communications and events. But probably the best way is, or one of the main ways, is using promises. So you may have come across or heard of promises in other languages. So JavaScript has recently got the Q spec with that and the thenable things. So that's one form of promises. Other languages have promises. Scala has promises. One distinction that I have to make really clear here is that when I say promise, so is the distinction between promise and future. Now, actually, the words can mean exactly the same thing. So a promise is a value that you're promising to make available in the future, and a future is a value that's going to be made available in the future. But in Java, the word future was already taken by Java util concurrent future. And while that, yes, is a abstraction for a value that will be available in the future, the problem with it is the only way to get it, or to read that value in any way, is to call the get method on it. And that requires blocking. So for that reason, I'm not going to be talking about Java util concurrent future at all, and you need to, when thinking about asynchronous development, reactive development, you need to completely divorce your mind from or unlearn anything that you've ever learnt about Java util concurrent future, because it's simply not helpful. So what are promises then? So a promise is something a value that's promised to be made available in the future, and the way you interact with it is by attaching callbacks to it. And typically these callbacks are in the form of a map call, or to change the value to something else when it's available, or what we call a flat map call, where in future it's going to be another operation that returns a promise is going to be done. And so these promises get composed together by doing these calls asynchronously. So in Java 8, there is a promise API. It has a little bit of a weird name. It's completion stage. So completion stage, it's an interface, and there's one subclass or one class that implements it in the JDK called completable future. The difference between completable future and completion stage, apart from completion stage being the interface, with completable future you can complete it. So you can say, I want this to be completed now, whereas completion stage doesn't offer you that method. And this is very important for writing APIs, because when you return a promise of something, you're promising the caller that you're going to give them a value. You don't want them to supply that value for themselves, because if they do, it could interfere with what you're doing. So we're going to talk a lot about completion stage today, but we're also going to look at a few other APIs. But for now, let's have a look at a demo of what using completion stage looks like. So we're going to write today a baking application. We're going to kind of represent a baker, and bakers bake bread. So this baker, he actually wants to bake the freshest bread in the world. And so he's got this method here, order sliced bread. Actually, I'm looking at the wrong one there. Get sliced bread. And so that's going to get the user, the caller, some sliced bread. And to do that, he needs to order some flour from a miller, and he'll also need to bake the bread in an oven. Now, looking at this miller interface here, we can see that when you order some flour from the miller doesn't return that flour immediately. It returns completion stage. And I'm going to use the words completion stage and promise exchangeably, but I'll probably say promise more often because it's shorter than completion stage. So the miller returns a promise for some flour. It doesn't return the flour immediately. Similarly, when the baker bakes the bread, the oven obviously takes time to bake the bread. It doesn't do it instantly. So the oven also returns a promise for some bread when you give it some dough. So let's have a look at a first implementation of our baker when you get, got the wrong one open here again, when you get sliced bread. So this one is going to return sliced bread immediately. So we call that order flour method on the miller, and we get our flour order, and then we're going to wait for it to finish. So there's actually no method on completion stage to wait, but completable future implements Java util concurrent future. So when you convert it to that, we can call get on it and we get our flour. And then having got our flour, we make some dough, and then we give it to the oven, and the oven returns the promise for some bread. And then again, we wait for that to happen, and so now we've got our bread, and then we slice it, and so we've got our sliced bread, and then we can give it to the customer. So a problem with this is that at these calls here, get, when we do this get on the promises, the baker is having to wait for things to be done. The baker could have, after ordering the flour, fulfilled another customer order. Maybe they had some dough that needed to be made from something else. They could have been doing that, but they couldn't do that because they were sitting here waiting for the flour order to be fulfilled, which is obviously very inefficient. No baker would sit there, do the order, and then stand around waiting for more flour to come, or stand around just watching the oven, waiting for it to be baked. So this is a blocking imperative implementation, and it doesn't use the baker efficiently. So what does a reactive version look like? So first I'm going to show you some Java 6 syntax, or Java 5, or anything other than Java 8. So again, we order our flour, and then we use this then apply method. So then apply is, if you've ever looked at any functional programming, is equivalent to a map. So what then apply does is it takes a function that will take the result, the promised value, and return a new value, and then the result of the then apply method will be a promise for that new type. So in this case, we've got a function that takes the flour and returns the dough, and as a result, we get a new promise for the dough. So that's then apply. Now then when we bake it, place it in the oven, now if we were to use then apply, then because the oven returns, when you bake dough, returns a promise itself, we would end up with a promise of bread, which is not what we want. We just want a promise of bread. And so to do that, we use then compose. And so like then apply, then compose takes a function that accepts the type of the promise, but this time instead of returning the new value, it returns a promise of the new value. And then inside the implementation of then compose, it's able to flatten that so that it can just return a promise of that new value. So now we've asynchronously baked the dough, and we've got a promise for bread. And then finally, we want to slice the bread, and this is doing a then apply again. So we take a function that takes the bread, returns sliced bread, we can slice it, and we finish up with a promise for sliced bread. And then we can return that sliced bread order. So at the top here we saw that we were returning a promise for sliced bread. So this method will actually execute very fast, in the order of microseconds. But once it's finished, the bread won't be baked. We'll just have a promise for the bread that the customer can then do what they want with. But this syntax is very ugly. If you compare it to the blocking version, which is very easy to read, and I've used a lot more intermediate variables than I needed to. It could have been even simpler than this. This is very ugly, and so that's where Java 8 comes in. Java 8 lambdas give a way of replacing all these anonymous inner classes with some very easy to read code. So let's have a look. We've got a simpler implementation here. So here we've got our promise for flour, and then I'll move this across. When we want to make our dough, we pass in this lambda here. And this lambda basically is exactly the same, translates to something that's pretty much the same as this function anonymous inner class here. So you can see we declare the argument. The argument is flour, and if it's just one line, we don't even have to have a return statement. It will return that the result of that expression. Similarly, we then compose. We take the dough, we pass it to the oven, and that will return the promise for bread. And then to slice the bread, it's again the same thing. Now, if these methods were a bit more complex, which they can be, so I can, for example, put some curly braces there, and then I can do other things inside this lambda. Such as printing stuff out or whatever, and often you'll need to do that. So the lambdas can be quite complex, but in this case they're actually not that complex because we're just, in each case, we're just returning invoking a single method with the argument that's passed in. And because of that, we can actually simplify all these lambdas even more, because Java 8 has a syntax for something called method references. So we can see here, in here all we're doing is invoking the dough constructor. So to refer to the dough constructor with a method reference, we use this : syntax new. And so that there translates to exactly the same as what this translates to. It's just a simpler syntax. And again, we are baking the dough by referring to the bake dough method on oven. So you can actually get a method reference on a local variable, or in this case it's a field in the class. And then in this one, we're passing the bread .slice method. And because this bread, because the bread has a type of bread, we can actually refer to the method that's on the object that's been passed into us and have that invoked. So this is a much simpler syntax. And in fact, one problem with lambdas is that they can, because of the anonymous inner classes, they can make the stack traces look a little ugly. So if you can make all the code that you want to do in these callbacks extracted out into a single method and then just use this syntax, you'll actually end up with something that has nicer stack traces and is probably a lot easier to read. Now, of course, completion stage is a fluent API, so each of these returns a new completion stage. So that means we can, if we want, even simplify it further, and that's our final implementation. This red underlining here, I think, is a bug in IntelliJ. We know that works because it works up here. But yeah, that's essentially what it looks like to create the sliced bread asynchronously. So there's a few other features of completion stage that I'd like to show you. So in this case, what happens, let's say the miller can't fulfill the order. Maybe his mill has broken down, or he crashed on the way to delivering it, and through an exception. So completion stage has a method on it called exceptionally, and what it lets you do is recover from an exception condition. So it will take a function that takes the exception that was thrown, and let you return a new value of the same type to be able to recover from it. So our baker has some emergency flour for in case the miller is unable to fulfill the order, and so he's going to, if the miller does throw an exception, he's going to return that emergency flour instead. And again, so you can see here, the result is still a promise for flour. And so you could use that at every stage. I mean, if the oven broke down, you could go and use a different oven to bake it, or if the knife broke when you were slicing the bread or whatever, you could recover then. Okay, another thing, sometimes you want to do multiple things in parallel. So if we, let's say the baker's decided to step up the level of freshness and it actually orders fresh yeast. I know that actually doesn't make sense because they tend to keep a culture growing, but let's just pretend. And orders fresh yeast when they want the bread. Now you could, because order yeast also returns a promise for yeast, you could then compose the order for the flour and then have your with a new order for yeast, and then have your yeast and flour order there. But you don't really want to do these things. I mean, a baker wouldn't do those things one at a time. He wouldn't wait for the flour order to be fulfilled before ordering the yeast. He would do both at the same time. So you can see here, we're doing both. We've done the flour order and the yeast order, and they're going to go and happen off in the background somewhere. But in the meantime, what we can do is use this then combine method, and that allows us to, so we're saying, take the flour order and combine it with a yeast order, and then we can pass in a function that takes the flour and yeast arguments and convert them to a list. And so now we've got a list of ingredients. And it just so happens that our dough constructor also accepts a list of ingredients, so we can now use that and bake the dough and slice the bread. Okay, so that's completion stage. Now, as I said, I'm a developer on Play Framework, and one issue that a lot of framework developers have when looking at something like completion stage is that not everybody is moving to Java 8 yet. And so if we move to Java 8 right now, then that means dropping support for Java 6 and Java 7. So, so for that reason, we can't fully embrace completion stage yet. And each framework will obviously have its own way of addressing this, but in Play, the way we actually already have a promise API that we've had since Play 2.0 was released. So we can continue using that. So what I'm going to show you now is that promise API, and one of the interesting things about the Play promise API is that it's more idiomatic compared to other languages, and also other features in JDK 8 such as streams and optional. So in here, I've got a Play promise-based implementation of our baker. So this time the type is promise, which is a type provided by Play. It comes from play.libs.f, F standing for functional. And so we order the flour, obviously that returns a promise. And then instead of calling .then apply, we call map. And so if you've had a look at JDK 8 streams, or JDK 8 optional, or if you've done Haskell, or if you've looked at some of the ECMAScript 5 or 6, I think, new functional methods that allow you to map. Map is a very common term for converting the value of some sort of container type, such as a promise or a list, into a new type underneath that container type. So it's exactly the same thing semantically as then apply, but it's a simpler method to write, and I think simpler to kind of understand. You're mapping the value inside the promise to a new value. And then there's also, instead of then compose, we've got this flat map method. So flat map is like map. If I were to just use map here to explain why it's called flat map, if I just did dough.map oven bake dough, what I would end up with is a promise for a promise of bread, which I don't want because it doesn't make sense to promise a promise of something. And so what flat map, where the flat comes from, is that you flatten that promise of a promise into a single promise. So that's flat map. And again, flat map is a common method. You'll see it used on JDK8 streams. You'll see it used in JDK8 optional. You'll see it used in Scala and a number of other languages. And so again, I use the map method here. Similarly, here's the fluent version. So as you can see, it's quite simple to read. Okay, but what does this actually look like when you use it in play? So you can see here, I've returned a promise for sliced bread, but what does the consumer do with it? I mean, eventually you have to actually do something with a value. You don't want to keep on mapping and mapping and mapping it. You want to do something with it. And the answer to that is usually in the framework. So in play, HTTP requests are handled by controllers. And so here I have an action, and it returns, and this will be invoked by play when a request comes in for whatever URL this action is matched to, and it returns the promise of a result back to play. Now then play will do its own thing to handle that, and you typically do some I/O to be able to write the response out. But as an end user, it should be very rare for you to want to do anything other than map, flat map, or recover or things like that. You should never actually need to add a callback or get or wait for the result of a promise. You always should let the framework pass the promise back to the framework and let it handle it. So you can see here we're ordering our sliced bread, and then play expects a promise of a result because the result is what it sends to the HTTP response. So we map that to a result, and so it's going to be an OK result, and we serialize the sliced bread to JSON. And so there we have our result promise, and we return that back to play. Maybe a bit more realistic, not just doing our baking bread API, is if you want to do a web service call, a REST API call. So let's say our baker has a REST API, baker.com, where you can get sliced bread. So Play has an HTTP client, which we call WS. You pass in the URL, and then the get, that's not a get as in a future.get, that's a get as in execute the get method, get HTTP method. And that returns a promise for a response. And then, of course, we want the promise of results, so what do? We map it to an OK result as JSON. Of course, this is an excellent example of when an exception might happen. Maybe you might get a failure code or something like that. And so here we could also do, in the play promise API, it's called recover, and pass a function to be able to handle that exception to do something else. In fact, in this case, we might end up returning a 500 code or something like that. And here's another one, which, so in this case, what I'm showing is what it might look like. So doing a call on a REST API directly from an action is probably not very good because it means that your action is not testable. Usually you want to pull stuff like that out into another interface. And so you might have this interface here for ordering sliced bread, and just imagine that this is in some sort of baker service somewhere, and it will let you and so then instead of mapping it to a result here, we can map it to a promise of sliced bread by parsing it as JSON. So this is what it might look like to write an API that works with promises. One last thing I think that I'm showing here. So let's say you've got a very expensive CPU operation, such as wanting to count to, I think this is 1 trillion. This can be very easily dispatched to the background. So obviously you wouldn't create the executor in the action itself. You would have that stored globally, but I've got it just here so you can see it. So we've got an executor, and when we the play promise API lets you create a new promise by calling this promise method, and you pass in a callback that's going to be executed. It's not executed immediately. Rather, you also pass in the execution context in which you want to execute it, and then that callback will be executed in that execution context, which is in our case, a single thread executor. So this will count to 1 trillion in a background thread. In fact, it's actually summing all the numbers from 1 to 1 trillion, which I guess will overflow, but then we can map that to a result. Okay, so now we've seen what it looks like in play, and we've learned if you are a baker, one more thing that I want to talk about before I go on is another method for doing asynchronous, handling asynchronous events that isn't promises, and this is using actors. So let's say we want to implement our miller. So has anybody here heard of Akka before? Okay, so Akka is an actor system, and actors are, I guess, units of behavior that kind of interact with each other asynchronously. So you might have a miller actor. An actor sends and receives messages, and so we've defined a message here called order flower. The convention in Java for defining the interface to an actor is to have a class called the actor protocol for that thing, and then put all the messages that can receive inside that class. So we've got this order flower message, and then our miller actor is an Akka actor. It's got a linked list of bags of flour, and it's also got an actor ref for the mill. So when our miller receives an order flower message, so actors are untyped, they come in as objects, so you need to check if it's find out what instance the message is. If our bags of flour is empty, then we're simply going to forward this request onto the mill actor. But otherwise, we will take the first element off the bags of flour and send it to the sender, whoever requested us the flour from us. So this is reactive because in here you never actually ask for anything. All you do is handle messages in onReceive. It's important to note that actors ensure that their state is accessed in a thread-safe manner. So we don't have to worry about using a concurrent structure here. It's perfectly fine to use a mutable linked list that I'm doing. And so that will let us to just talk to that and modify it in the onReceive method, because the onReceive method will only ever be invoked once at a time. And so how is this actor then used? So I've got an implementation of the Miller API. So obviously we want we have to implement this order flower method. So Akka has a concept of doing an ask, where you can ask an actor for something, and then it'll return a promise of whatever that actor sends back to the sender. So you can see in the actor we sent the message back to the sender. So when we ask that, we ask the Miller actor, we send the creator order flower message, and then this here, Akka will actually not let you ask for anything without setting a timeout. So it's one of the features of Akka is that it doesn't let you do things that could fail without cleaning them up. So we've got our future. Now Akka is primarily a Scala library, though it does have support for Java, but it returns a Scala future, which is very similar to a play promise. But to make it easier to work with, we'll simply wrap it in a play promise. So now we've got a promise of object. And like I said, actors are untyped, so the message we get back is object, and we want to map that to cast it to flower. So that's how you might interact with Akka. Okay, so now you know, if you're a baker, how you can write a reactive application. How many people here are bakers? A couple. For the rest of us that are in the real world, actually I spent a lot of time on that transition, so I'll just do it again, make it worth it. And again. Okay, so we have the real world here. What does this look like in an actual application? So I've got one last demo for you, and okay, it's not quite a real-world application, but it is much bigger and probably a lot easier to relate to than all my baker examples. And what better to demo a real-world scenario than to actually show the world itself? So I've got this application called Reactive Maps. Now before I'll show you it. So you can see here, here's me. I'm in Philadelphia. And what this application does is when you connect to it, it simply sends your location, and then you can see the location of everyone else that's connected to it. It's sponsored by the NSA, but don't worry about that. So obviously it's pretty boring just looking at, because I'm running this locally, the only person connected is just me. So it's pretty boring just looking at that. So I've actually got some bots. I pulled some GeoJSON data from the North Carolina hiking website. And so we've got some bots that are kind of walking around North Carolina here. We can zoom in on them. And you can see when you're zoomed out, it clusters the markers together so that you're not overwhelmed with too much data. So we can see these bots here walking around and click on them. So this application is a reactive application. It sends updates to the user in real time. The user doesn't have to request them, they just come. You can actually, so if what I explained today is going too fast for you, or if you want to go back and have a look at have a closer look, you can actually get this demo application. If you go to TypeSafe Activator templates, you can find this Reactive Maps Java 8, and you can download this template bundle, and that will give you TypeSafe Activator, which is a way that we have at TypeSafe of learning applications. So after running that, you'll get this screen here, which lets you, which has a tutorial in it. And what I'm actually going to go through today, so this tutorial shows you can have a look at some of the code. It's interactive. And what I'm going to do today is just go through a few steps of the tutorial where it's getting us to implement a new feature. I've actually done most of the tutorial already to get the boring bits, like the that aren't really relative to Java, that aren't really relevant to Java 8. But we're going to do a few of the bits that I haven't done. So, if you're interested in seeing this reactive application with Java 8, you can go and download this yourself and follow the tutorial. But what we're going to do is we're going to add a new feature, and so they're all moving because of the way that Chrome buffers WebSocket messages. You can see here that there's this status here of how far the bot has travelled, and it says it's travelled 10 metres. In fact, if you look at them all, they're all travelled 10 metres, and that's because I've hard-coded a result of 10 metres in the back end. So we want to get rid of this hard coding and actually implement this feature properly. So we'll start off in an actor. So this is primarily an actor application, and we've got this user metadata actor, and you can see here we've got this map, which is a map of user IDs to the last position they were seen at and the distance they've travelled so far. And we have this onReceive method to be able to handle some messages. So the first thing that we'll implement is a get user message. So here I'm saying, if the message is a get user message, then we'll try and get them out of the map. If they're not null, then we can send their distance back. If they are null, we're just going to say this user has travelled 0 metres. We're not going to worry about handling that, handling if they're not there. And then the other thing that we've implemented is what happens when the user's position is updated. So if the message is an update user position message, then get them out of the map. If they're not null, then we can calculate the distance between the last point they were seen at and the current point that the update is for, and put that into the map. Otherwise, we'll put them into the map with a distance of 0 and with their current position as the last position. And so we can save that. And the other thing that I need to implement is asking that actor for the distance. So I've already implemented the stuff that sends these update user positions, but we've got this user controller here, and you can see the hard-coded 10 being returned there. So I'll delete that. And as I showed before, the first thing we need to do is, I'll get rid of that. Oh, every time I do something, it's... So you can see here the first thing is I ask the actor, the user metadata actor for the user, and I get back a promise of object or I get back a feature that I've wrapped in a promise. And then I can map that answer. First I cast it to a user, and then I can serialize that user to JSON. Okay, and so we should be able to save that. And if I refresh this, I hope it works. I've got a compiler error. I must have missed something out there. Where am I? So we've got a compile error here. Can anybody see? That's right. I've got to change this to return a promise of result, because before it was returning the result immediately. So we return a promise of result, and we can now map that answer, save, and if we refresh now, Just taking its time to start. There it is. So once those bots get warmed up and start sending their data, we should be able to see them. And we can click on them and see that one's travelled 82 metres. And click on it again, it's travelled 120 metres. Very fast bot, these hikers are very fast. So there you can see an application of what this looks like using Akka to manage some state asynchronously, and then querying that using promises from play. So, I told you all that I'd put you to sleep by talking about monads at the end of this. Hand up here if you know what a monad is. Okay, good, not many of you. Hand up if monads are this mystical thing that functional developers have always talked about, that you've heard about, and you don't really know or probably even care what they are. A few. So the first half of this presentation I actually gave before I knew what a monad was, and then a few weeks later I was talking to somebody and I told them I don't know what a monad was, and they said, but you just gave a presentation about monads. Monads are actually really simple. If we go back to our baker, and we've got this flat map method here, that flat map method is actually all a monad is. Anything that has a method that looks like flat map, or in the case of completion stage, then compose. So in other words, a method that takes a function in other words, something that is a container of something and takes a function that takes its type and returns a new container of a new type, then that's a monad. So in this case, monad, what we're working with here is called the promise monad. It's able to chain promises together, but there's also, in the JDK8, there's a streams monad where you can, because that's got a flat map method, so you can take elements from the stream and get new streams as a result that are all put together into one stream. And that's all monads are. So if you're wondering what monads was and wasn't sure what all the fuss was about, really there's not much fuss about them, it's just that flat map method. So, that's all I wanted to say today about reactive web development in Java 8. Anybody have any questions? None? Okay, well, thank you.